So this is the third video about convergence of sequences of functions to some limit. In the first video, we talked about a naive notion of convergence, pointwise convergence. In the second video, we talked about a stronger notion of convergence, uniform convergence, and we showed that lots of nice properties happen when you had uniform convergence. Continuous functions converge to continuous functions, derivatives converge to derivatives, and integrals converge to integrals. In this last video, we're going to put some of this together and use these notions of convergence to prove some formulas that I think are substantially less obvious than anything we've seen so far in these videos. We still need to do a little bit of throat clearing to get some notions out of the way. So here's a definition of a uniformly Cauchy sequence of functions. We say that a sequence of functions is uniformly Cauchy if, for all epsilon greater than 0, there exists some capital N, so that for all little n and little m bigger than capital N, and all x and a, the difference between fm of x and fn of x is less than epsilon. All right, that's sort of a long definition, but it should be somewhat familiar to you, right? We're talking about Cauchy sequences, and what that means is for all little m sufficiently large, the difference between the mth term of the sequence and the mth term of the sequence is small. We say that this is uniformly Cauchy for the same reason that we talk about uniform convergence. It's that this epsilon comes before the choice of the point x. Okay, so this should be a not terribly surprising definition, even though it's a long one. Then we get the following immediate theorem, the Cauchy Criterion. Suppose that fn is a sequence of functions, then the sequence converges uniformly if and only if the sequence is uniformly Cauchy. Okay. I'm not going to give the proof of this, it's certainly in the lecture notes, but it's very, very similar to previous things that we've called Cauchy criteria. Okay, great. What I'm going to do instead is talking about an immediate consequence of the Cauchy criterion, which is going to be quite useful when talking about convergence of sequences. So I'm going to fix some sequence fk of functions, and I'm going to let mk be a sequence of positive real numbers. If mk has two properties, it's a summable sequence, that is, the sum from k equals 0 to infinity of mk converges, and it's an upper bound for the norm of the fk's, then the partial sum k equals 1 to infinity of fk converges uniformly. Okay, what's this saying? This is saying the following. If we have a partial sum of functions and the individual functions are small, what does small mean? It means small enough that the sum of the norm converges, then in fact the original partial sum itself also converges. An even shorter way of saying that is that in order to get uniform convergence of a sequence of functions, it's enough to talk about convergence of their norms. So that's a pretty nice thing to do, because talking about convergence of functions is hard, but convergence of numbers, well, that's something we've been doing for a long time. What's the proof? Well, it's not going to be a whole lot longer than that preamble. I define Sn to be the partial sum associated with the sequence fk, and we're going to show that that sequence is in fact uniformly Cauchy. Fix epsilon greater than 0. Since this whole sum converges, there exists some capital N, so that for all little n greater than capital N, the sum from k equals m plus 1 to n of mk is less than epsilon, right? Why is that true? Well, this is a convergent sequence, therefore it's a Cauchy sequence, therefore it has this property. If we choose exactly the same little m and the little n, then the difference between these partial sums, Sn of x minus Sm of x, is equal to exactly the norm of this partial sum here, and using the triangle inequality, that's less than the sum of the mk's, and using this inequality here, that's less than epsilon. So what have we just done? We've checked for all mn bigger than n, we see that this sequence here, Sn of x minus Sm of x, is less than epsilon. That's exactly saying that Sn is uniformly Cauchy, hence by the previous theorem, it's uniformly convergent. Okay, so this is a pretty simple theorem. It's a lot like our previous Cauchy stuff, but it turns out to be extremely useful, basically because it's hard to talk about partial sums of functions, and much easier usually to talk about partial sums of norms, so this is sort of the easiest way to check that sums of functions converge. Let's actually use that in order to find something that's interesting. So just as a bit of a recap, here's something that we know about infinite sum formulas. We know that the sum from k equals 0 to infinity of x to the k is in fact equal to 1 over 1 minus x, for all x strictly between minus 1 and 1. So this is an infinite sum formula, and this one is sort of a fairly common one. It's one that you may have shown, in high school, and certainly that we've seen a few times in university, but it's not a terribly hard one to derive. And you might think, if you see a formula along these lines, that you might be able to use this to find new infinite sum formulas by just differentiating both sides. There's a sort of an obvious thing that you might try, right? So if you want to find, for example, the infinite sum formula for 1 over 1 minus x squared, well, we note that the derivative of 1 over 1 minus x is 1 over 1 minus x squared. And so you might sort of hope that you can take the derivative here and the derivative here and get the same answer on both sides. And we're going to see that that's true, but there's sort of a technical obstacle that might make you a little bit worried. If I take the derivative of 1 over 1 minus x, okay, certainly I get 1 over 1 minus x squared. If I take the derivative of this infinite sum, well, it's not so obvious how to do that and get something that's useful. And so what we really want to do is move that derivative inside. So that is, we want to sort of check that the derivative of this sum is equal to the sum of the derivatives. It's not so obvious that that's true, but if it were true, well, then we can move the derivative inside. We could take the derivative of this polynomial. That's easy. And we would check that actually we got this infinite sequence. Let's put all of the last few minutes together, right? We know certain infinite sum formulas, like this one, but we don't know very many of them. One way that we might try to come up with new infinite sum formulas is take one of the easy ones, and then do something like differentiating both sides or integrating both sides. And that sort of almost works, but there's one step in that idea which is something that needs to be justified, which is how do you move a derivative from outside of the infinite sum to inside the infinite sum? And it turns out the stuff that we just did is exactly what's going to let us do that. How do we do it? Well, we're going to look at some interval like minus 1 plus epsilon to 1 minus epsilon for some fixed epsilon greater than 0. And we're going to apply this big long theorem that we saw in the last video. I'm not going to read the whole thing out, but the important one here is that it gives us a formula for derivatives. It tells us that the derivative of a limit object is equal to the limit of the derivatives under, well, a whole bunch of conditions. How are we going to apply this? We're going to apply this to the partial sum fn of x is equal to the sum k equals 0 to n of x to the k. If we want to use this theorem, we have to check all of the conditions, and also, of course, we need to find a formula at the end. So what we need to do, we need to check that fn has a continuous derivative. We need to check that fn prime converges uniformly to something. We need to check that fn converges pointwise to f, the function 1 over 1 minus x. And we need to actually find f prime, the thing that fn prime converges to. So we're going to prove all 4 of these things in relatively short order. Actually, some of them are pretty clear. We want to check that fn has continuous derivatives. Well, we can just write that down, right? It's a sum of polynomial terms. That is, it's a polynomial itself. So certainly we know that polynomials have derivatives. So A, check. That one was fairly easy. Next, we have to check that fn prime converges uniformly to something. And this is sort of the most technically demanding one, sort of in theory, but actually for this example, we can just use the m-test. We do have to be a little bit careful, but let's see what happens. We want to use the m-test, that is, we want to bound the size of these terms here. How do we do that? Well, we note that k times x to the k minus 1 is less than k times 1 minus epsilon, absolute value, to the k minus 1. And so if you look at the sum from k equals 0 to infinity of this bound, what you get is the sum from k equals 0 to infinity of k times 1 minus epsilon to the k minus 1. This is going to 0 exponentially quickly. This is going to infinity only linearly quickly. And so we can check that, in fact, that sum converges. So since this sum converges, by the m-test, we know that, in fact, fn prime converges uniformly to something. That's sort of a fun thing. I want to point out this is the first time, at least in the videos, that we've checked that a function converges uniformly to something without having any idea what it converges to. All right. Next up, part C. So part B, also check. Part C, we want to check what fn converges to. We've already seen this before, actually, but I'll do a quick recap. Fn of x is equal to the sum from k equals 0 to n of x to the k, and we have a formula for that. Partial sum, it's just this thing. And it's easy to check by looking at the individual terms that all of them survive and stay the same as n goes to infinity, except for this one, which goes to 0. And so indeed, fn of x converges to 1 over 1 minus x, which is what we sort of hoped. And then finally, we need to find f prime. Well, that's easy. We have a formula for f of x, and so f prime of x is equal to 1 over 1 minus x squared. So this was a lot of stuff to do, but it actually didn't take us all that long, not just because I was speaking somewhat quickly, but actually each of these individual proofs were quite short. The hardest was B, but actually the M test let us do it very, very quickly. If we put all of this together, we know that for fixed epsilon greater than 0, then from x on that interval from -1 plus epsilon to 1 minus epsilon, the sum from k equals 1 to n of kx to the k minus 1 converges uniformly to 1 over 1 minus x squared. So we have this really nice infinite sum identity for 1 over 1 minus x squared, and that's one that's probably not that much fun to prove sort of by hand, right? It's not so easy to come up with an actual formula for this thing without using this derivative. Now, to put sort of the last little step in this, we did this for fixed epsilon greater than 0, and we got uniform convergence. But since epsilon greater than 0 was arbitrary, and we have convergence to the same formula here in terms of x, what we know is, in fact, that this sum converges at least pointwise to 1 over 1 minus x squared for every x in the interval -1 to 1. Okay, so that was sort of nice. We managed to use all of this machinery that we built up to prove a formula that probably wasn't terribly obvious. And that's it for convergence of sequences in general. Thanks.